now we're gonna derive the final form. Hope that we can derive the final form now. Last stop, we actually stopped at here. This is our PVD for our beam. Alright, just take in this thing over here. Alright, just paste it there. It's the same thing. I didn't cheat your feeling. Alright, well, you know that your D over K, alright, is your EI over R. Okay, is your flexure equation or whatever. Alright, but anyway, let's continue. Alright, now we know that what is it? Alright, this is our PVD, right? Now we are gonna expand your K as BT U2I and your K virtual as your BT blah blah. Okay, so our purpose now is to do this first, and what we see is that we know that the strain is equals to BT UI. Alright, what is this BT UI? Is that this thing. Alright, and we know that, and this thing, if you were to expand, you're talking about N1 U1 plus N2 U2 is equals to your U, and U is just your displacement. But in this case, we assume that the displacement is your strain, and therefore it's just a small strain displacement, that's all. Okay, so be careful of this notation. Alright, and this is just a strain displacement relationship. Alright, let me do our little stuff. Hold on a while. Never mind. So your BT dot UI, alright, well, like got love only, but anyway, so BT UI is this one, and therefore, I mean, for bar structures is BT UI, for beam structure is BT dot U2 UI, I mean U2I. Okay, so I repeat again, for the bar is this one over here, N1 U1 plus N2 U2 is equals to U, or is equals to epsilon, your strain. This is for the bar system. For the beam, then you're gonna write in terms of this system. Alright, we're gonna not derive it, but just take in what we need to know. Alright, where you need to know that your K is equals to your this one. Alright, because 1 over R. Alright, your K is 1 over your curvature. Alright, or is theta. Alright, so 1 over R is equals to theta. Alright, where is also your 1 over R is also your curvature, your arc length. Okay, so your arc length itself is a d2u dx square. Right, it's because it's a quadratic equation. So your curvature also over here is a quadratic, and therefore it's d2u dx square, you can assume. And therefore, we just write this u2 out. So therefore, you have a where your u2 is equals to some nt dot u2i. Okay. So K, as you know, is this one already. Alright, is your stuff. So I'll just simply take out the U2 and just plug it over here. Same thing, the rest didn't change, the rest isn't. So I'm just taking the U2 out only. Okay? And taking note that U2 is equals to this one, which is some shape function multiplied by its like displacement and things like that. Alright, so if I were to sub in U2, alright, as this one, alright, this is U2, I sub in as this one, okay, then I can simply multiply it in. Alright, this thing I can multiply with my n, my shape function n. Alright, what I have is this one. Okay, so it's like d square dx square. Alright, and then n, I'll just put it over here. Because nt is just a transpose, alright, just taking n only, because I just take it n will do that. Okay, so what you have is this one, which is your strain displacement system. Okay, so therefore what you have, this whole thing will become your B or BT. Okay, so far so good. As you see, this is NT, so now we have BT. If just take note of it lah. Okay, just it's not complicated, but it's just like rewriting the stuff. Like for example, d2 dx square n1 and then n d2 dx square n2. Alright, so this thing over here is your nt. Okay, I mean it's your bt. Okay, so d2 dx square multiplied by n1 n2 is equals to d2 dx square n t. So I think we should write t over here. But anyway, at least you get what I mean. It's something of that meaning. Nonetheless, we have proved to you that bt.u2 is actually this one. This one is b transpose. The rest are the same. Alright, but we haven't defined our u2 yet, and we don't even know our shape functions yet. Okay, but at least we get to know that at least the strain is a different equation again. Alright, with other stuff. In our case now, it's a second order. Okay, so therefore I'll just paste this thing. I'll just paste it over here. Okay, it's the same thing as you can see. I didn't cheat your filling. Just paste it over here. Okay, as you can see now, your u is there is somewhat your at node 2. Okay, you have four degrees of freedom, if so to speak, degree of freedom. For 4 degree of freedom, you need 4 shape function. For 2 degree of freedom, like your bar, because it's just u1 and u2. Okay, or I think correct, u1 and u2. So you have only n1 and n2. For our case, we have like a u2 at node 1, or in other words, this is something like a u1 and u2. Okay, but I don't know why. But anyway, let's just take it first. Alright, so it's u2 at node 1. So at node 1 is this one. At node 2 is this one. Okay, and you have a theta, your angle, and the angle over here. Theta 1, 2 at node 1 and node 2. So I think this is pretty familiar, so I'll not go through quite detail over here. At least you get to know all this. Alright, so you just know that your u is in terms of all this, and your shape functions must be correspondingly in terms of its own nodes, like u2 at node 1, at node 1, 1, 2 at one direction. So I think u2 in our case right now, alright, is in terms of telling us that we have a direction in the 2 direction and 1 direction. Okay, so the first number over here, be kind of careful of that. So the u2 tells us that is some displacement in the two direction. Alright, if you remember the sigma 11, sigma 22 is just that meaning. It's just in the 1 direction or 2 direction. In this case, it's 2 direction. Okay, so therefore, we're gonna evaluate these shape functions by in a very quicker way. Alright, so for the shape functions, we're gonna use a Cupid polynomial, meaning it's in terms of a cube, or some c cube. If you remember the other time, we derive from the u to the x to the c. Alright, this is for the bar element. Alright, the bar element actually deals with a lot of stuff, and kind of messy, but at least you know that where is the c coming from. This c is just related to this c in a different mapping only. Okay, while the equations over here, cube, square, everything over here, is very similar to the first few videos that I just started. Alright, you can watch the l9v7. Alright, another way to derive using the first order equation. In our case, as you can see, we are dealing with a third order equation. Alright, third order equation. So I'll not go into details on how to prove to you, but at least you can see that there is few variations. Right, the first 2 variants, I would say. One variation is going in this manner, alright, or is going in this manner if n2, or you can have 1, 2 and 1, 2 over here. Okay, as you can see, it's 1, 2 and 1, 2. The curvature is slightly different, but I just need to take note of how to use this thing. These are all your shape functions to tell you how does the shape of the beam looks like. Okay, and that's all, right? And then take note of this thing is that I and j, when I is equals to j, you have 1. When I is not equals to j, is 0. If it's not familiar, this is just somewhat your Kronecker delta relationship. Alright, but anyway, let's continue first. Okay, just take note that your shape functions is all this equation, and that's all. You don't need to derive that, hopefully. So before I go into something, because we're ending soon, just let you know that this is our PVD. Okay, what we have done at the earlier part, maybe the first few minutes. This is our PVD. We show you that the K is equals to this one. Your K virtual is this one. Alright, we have shown you that K is this one. So likewise, the K virtual should be this one. Okay, I didn't show you virtual, but the virtual should be the same trend. Alright, just that your displacement is a virtual displacement u2. That's all. Okay. Next, what I'm gonna do now. Alright, so this is still your PVD. Alright, in a more detailed way, because it contains your B already, your shift functions and your strain displacement matrix, everything. Okay, so now we're gonna do is to replace your U2 virtual by a 4x4 I don't know what is it. I will highly feel that it is actually a 4x4 identity matrix, which is 1 1 1 1. The rest are 0. Okay, hopefully this is pretty clear. So therefore, at this stage right now, you can sub in your U2 as this one over here. Okay, while your U2 virtual, you also sub in as this one over here. Okay, while then your beta t, alright, is 1 times 4, because you know that there is four this strain displacement, right? There's dn1 dx, dn2 dx, dn3 dx, dn4 dx. Alright, this is your strain displacement, because you have 4 shape functions, right? We have shown you over here n1 and 1, things like that. Alright, while your u2i is your u2 at node 1, and then your theta 1 2 at node 1, u2 at node 2, theta 1 2 at 2. If you still remember, this is your u2. So it's in terms of a b, in terms of a transpose, so it's 1 times 4, and then if you have got your u2 over here as 4 times 1. Alright, so this is something that we have shown you just now. Over here is at the bottom over here. That's what we have shown you. Alright, where your BTU2, alright, K is equals to what? To all these things. Your UI and your N. Okay, or in other words, I think you get what I mean already lah, okay? About just a while ago, 7 minutes or 8 minutes, alright, at 7 or 8 minutes we started to talk about these things already. Because what we have shown you is all this. Right, all this things, all this understanding is for you to look at this over here. That's all. Alright, while we add in the definition of the virtual U2 as an identity matrix right now. Okay, so when you mix them all together, you have this equation over here. Okay, I hope that this is pretty clear. I hope that I didn't confuse you anything. Alright, as you can see, this is in terms of a minus. This is one bracket, this is another one. So I'll just simply bring this whole chunk over here to the other side. So if I were to do that, what you can see, alright, is that this thing over here is this thing, and then this thing still stays the same as over here. Okay, but taking note that it is 1 times 4 matrix, because this is just some identity matrix. Okay, alright, same thing over here. This is also 1 times 4, because it's just an identity matrix. So BT 1 times 4 multiplied by the identity matrix of 4 times 4. Alright, so these are the same, so therefore we are just taking 1 times 4. This is just some matrix rule. Alright, so we have 1 times 4. If it happens that you don't understand what I mean. Okay, while this part over here stays the same. Alright, so I'm simply merging this part and this part only. Okay, while this thing over here I leave it the same. You just think about it. Alright, we are almost there. So this one, now this is where we stop. Alright, and I gonna do something with it already, is that I gonna transpose this thing. Alright, now this is transpose. I'm gonna transpose this thing. So this thing is over here, I'm gonna transpose it. If I will transpose this whole thing, this transpose with this transpose, it becomes just like this. So if it's 4 times 4, if you transpose, you'll have 4 times 1. Okay, it's just a transpose already. So please be careful of the transpose rule. So if I were to transpose 1 times 4, I'll have 4 times 1. As you can see, that this thing will be removed, because transpose is equals to 1. Alright, that's all. Okay, and therefore this part over here is settled. Now next, let's see what we can do. Well, this thing over here, I'll let it stay the same, alright, because as you can see, this one is a inner function, because the t is inside. If you take note, BTU inner functions tells us that it is talking about a dot product with u. Okay, so therefore be kind of careful of this thing. So BT dot inner t is actually is a dot product. As you can see, it's dot product over here. So dot product will give you a scalar. So if you were to transpose a scalar, you're just getting back a scalar. For example, a scalar is just 5. If you transpose it, you also have 5 transpose. Alright, it's just the same thing. You're just switch, because there's only one number only ma. If let's say you have two numbers like 1, 2, if you transpose, you'll have 1, 2. Right? You know what I mean? So therefore, if it's a scalar, if you transpose, it's just a scalar, that's all. So just keep it as scalar first, just don't want to confuse you. While this t over here, you can transpose together. You can transpose this bt to a b, 4 times 1. And this is being reflected over here. Okay? Alright, that's why it's a little bit, yeah, here and there, but be kind of careful of it. Well, because they are just scalars, so when you transpose, they will still stay the same as this thing over here. Therefore, when you see this thing is over here, or this thing is over here. Okay, that's why it's kind of cool and it's kind of complex. So just hang on with it. All right, and therefore this thing over here is this thing. All right, it's gonna dyadic product with your BT first, where your D is gonna multiply it into here, because as you know, your D is together with this thing over here. So your D is over here. It's gonna dyadic product with your transpose of this one. So you're just simply rearranging only. So I rearrange this one to this one with relevance to transposing them. Alright, that's all. Okay, and then this U2 over here, just bring it behind while multiply with dx1 over here. Okay, so if I have to highlight properly, you see, these are all the stuff. You can just mix and match. Or just take note that the transpose will become transpose, especially for this one. Transpose will becomes this one. Alright. And the reason why, I need to repeat again, because I feel that it may confuse you, is that the reason why I didn't transpose this one is because this whole path over here is a dot product. You can't, when your dot product is a scalar can't be transposed. So the element of it still stays the same over here. When you transpose, it still stays the same. Alright, I've proved to you already. And therefore, this is why when you transpose, or you bring it over here, it's still the same element, it didn't transpose, is because it's a scalar as a whole over here. Hope that this is pretty clear to you. Alright, and therefore, just to rearrange, this is your stuff. Okay, so I've shown you after we transpose, we have this one over here. Okay, so we clear away all the 4 times 1, all of this stuff. Okay, to make things more easier to see. What do you have is this thing over here. Alright, your force is equals to your K dot U2I. Alright, this whole thing is your K matrix. Ta-da! Alright, so this is very different from the one that we are showing for the bar. The bar is simply L, like this. Alright, to be more strictly speaking, you should also write in terms of a dyadic. Why dyadic is because your B, alright, like for BT, your T is outside. Outside means it's the outer. Outer means it's a dyadic, and therefore you need to tell the person that this is the outer product. Alright, if it's an inner product, BTB, where your T is inside, alright, as you can see, T is outside, now it's inside, so it's an inner product, so therefore BT dot B, as you can see, they actually also show you, right, BT dot some other stuff, at least you, yeah. So when you write your test questions, please remember to write in terms of this thing. Be very mindful of that. Alright, so therefore I've proved to you this. So we're gonna in the next video we're gonna like roughly go through how how can we use this one to derive our stiffness matrix, because it's just some general formula only. Alright, and I shall see you there.